Alright, here is some more magnetism stuff for you. I'm going to begin talking about induction, electromagnetic induction. And to talk about induction, you have to remember flux. So I have some stuff written here about flux. A lot of this is exactly the same stuff that I had when I was introducing flux for Gauss's law. The general idea with flux is that it's a way of measuring how much field passes through a particular area. Now, of course, field lines themselves are not real. They're like a visualization. But you can think of flux as being a way of like counting how many lines pass through a patch or something like that. So I have a few different illustrations in the middle of the screen here. The most simple way to think about it is that you have some rectangular area. You can assign an area vector to that area. The magnitude of the area vector is equal to the scalar area of the patch itself. But then the direction of the vector is normal to the surface. So since I have this horizontal patch drawn there, the area vector points up. Conceivably, it could point down instead. So you have to decide which side is the top, sort of. But I have it oriented pointing up. And so if you want to know about the flux through this area here, because the area vector and the field, in this case it's an electric field, since they're parallel to each other, you can just multiply them together. So the flux would be E times A. But if there is some sort of an angle involved, in this middle case here, the area vector is perpendicular to the field. And so that means that none of the field actually penetrates through the surface. It runs along it, but none of the field passes through from one side to the other. So the flux here should be 0. And if you're at some intermediate angle, theta, then the value of the flux should also be intermediate. So there's a cosine involved when you do the calculation. And it's a little bit more general to think of it as being a dot product. So you have your field vector, you have your area vector. Take the dot product, that's the flux. But that definition, E dot A, is only useful if the field is uniform and the area is flat. So if you have some sort of a curved surface that you want to calculate the flux through, or if the field varies from place to place, then you have to adapt the definition a little bit into this integral form. And that's getting closer to the way that we used it for Gauss's law most of the time. And that's illustrated also in the middle. This electric field that I've drawn here is diverging. So the magnitude or the strength of the field is different in different places on my surface. So you just break the surface up into individual pixels basically. Each pixel is a tiny little area, dA. And you just calculate each flux for each little piece separately and add them together. That's what the integral does. So again, we previously only talked about electric flux, but you can do all the same stuff for magnetism, for magnetic fields. When it came to electricity, the reason we talked about flux was for the sake of Gauss's law, which you can see down there in the bottom left. When we did Gauss's law, we also drew that extra circle on the integral sign, just to indicate that the surface has to be closed in on itself. If you try to do Gauss's law with just a sheet of paper, like in my rectangular example up above, it doesn't work. It would have to be a cube. That would be okay. That has to be a closed shape. That's all the little circle means. If you were to try to do the exact same thing using magnetic fields instead of electric fields, you would find that the flux through a closed surface is always 0. And that is because magnetic fields, as I previously talked about, don't have ends. The field lines never originate or terminate anywhere. The field line either has to be infinitely long, or it can be some sort of a closed loop. But the point is that if you have a closed surface, like if you have a sphere, every magnetic field line that enters the sphere is also going to exit the sphere later. The only way that you could have a line go in that doesn't come back out again is if there were something equivalent to like a negatively charged particle with electricity. If I put a negatively charged particle inside the surface, I can have a line that goes in and never comes out. But there's no equivalent object with magnetism. Magnetism doesn't have monopoles, is what we call those. You can have a dipole, which would be like a north and a south pole close to each other, like an electric dipole that has a positive and a negative particle. But you can't have a north pole that doesn't have a south pole intrinsically associated with it. So there's no equivalent to positive and negative charges with magnetism, which means that although you can have, with electricity, a non-zero enclosed charge, you cannot have a non-zero enclosed poles, because every north pole has a south pole with it, and they can't be like separated from each other. I would encourage you to not really think about poles as being real in the first place, personally. The point is that the field lines, they don't have ends. And if the field lines don't end, then you can't have a non-zero flux with a closed surface. So anyway, magnetic flux, therefore, is not of much practical use for this purpose. If you do a magnetic version of Gauss's law, you can't really learn anything from it. However, magnetic flux is critical for electromagnetic induction, which is the way electric and magnetic fields can create each other. This is the way light works. It's the way most of our modern technology works as well, because we rely on electricity that is made by generators, and we also use that electricity to power motors, and all of that stuff involves transforming electricity and magnetism back and forth into each other. So induction is pretty important, and to explain how it works, you need to talk about magnetic flux. So what we already know from content that we've covered is that moving charges create magnetic fields. And there is another side to that, which is that if you have a moving or changing magnetic field, that can also create electric fields. It doesn't sound perfectly symmetric with the way I'm describing it right now, but if you continue to study physics, you'll find that there is basically a perfect symmetry to it, and we're just not talking about it in quite the right way in this particular course for that to be obvious. So there are two named laws about induction that are covered on the AP Physics C exams. They are Faraday's law and Lenz's law. I have them written out conceptually here. I'll show you the equation. In this video, I'm going to do mostly just conceptual stuff. There's not going to be really any math, but the equation is pretty simple. So Faraday's law states that a changing magnetic flux through a coil, so this is like a loop of wire or like a long slinky-like kind of thing called a solenoid. We talked about solenoids just recently. Any coil of wire, it could be just a single loop, or it could be many, many loops piled up on each other. But if the magnetic flux through a coil changes, you will get an EMF in the coil at the same time. That's the induction effect. You change the flux, creates an EMF. That's what induction means. So Faraday's law just states that this happens. Lenz's law is an extra detail to it, which is that the direction that the EMF goes, because just because I have a loop of wire and I change the flux and I get an EMF, that doesn't necessarily tell you, like, does the EMF go clockwise or does it go counterclockwise? Lenz's law is a way that you can reason through and figure out which way it's going to go. The direction of the induced EMF is such that the current that flows will produce a magnetic field that counteracts the original cause of the induction in the first place. Now that sounds really convoluted, and so it takes a lot of practice to get the chain of reasoning correct. But the basic idea is something happens to cause the induction to occur, and the direction of the induced current, or the induced EMF, counteracts or fights against the thing that caused it in the first place. So you'll see some examples of this, but like, if the reason that the induction occurs is that I am like pulling this wire out of a magnetic field. Suppose there's a magnetic field, I have a circuit inside there, and I'm like yanking the circuit out of the field. The direction of the induced current is going to be such that there's a force trying to hold it back inside the magnetic field. It like doesn't want the change to occur. And so the end result is going to be something that fights against whatever change was occurring. So mathematically, up at the top, this is just the same statements of the laws. Mathematically, the way we write Faraday's and Lenz's law together is like this. The big curly E is EMF, again, so that's measured in volts. The EMF is proportional to d phi dt. Capital Phi is the symbol for flux. I put a little b subscript on it, so you know it's a magnetic flux instead of an electric flux. But the core idea here is that the EMF is proportional to the rate of change of the flux. So the flux is changing fast, you get a strong EMF. If it's changing really slow, you get a weak EMF. There's also a capital N here. Just like when we saw solenoids recently, the capital N stands for the number of loops or turns or coils, how many times the wire goes around. A lot of the time it's just going to be one, but like in practice, if you're making like actual equipment to study induction, your equipment's probably going to have like dozens or hundreds of loops of wire to make the effect stronger. So that's what the N is. And then the minus sign is basically the Lenz's law part. That's what shows that the EMF is working oppositely to the flux change. Now, in some sources, and I should have looked this up, but I think that the AP Physics sheet, or formula sheet, is one of these sources. Some sources don't bother to put the capital N in there because they think of the big N as being part of the flux value instead. So like, I've been defining flux as integral B dot dA. But an alternative way of defining the flux would be N times integral B dot dA. And that kind of makes sense. Like, if you know that there are 100 loops of wire, then you might as well just say that the flux is 100 times bigger, because there's like 100 separate areas there effectively. So if you're defining your B that way, or sorry, your flux, if you're defining your flux that way, then you wouldn't want to put another n into Faraday's law, because then you would have 2 factors of n instead of only 1. So my point is, if you see Faraday's law written without a big N, that must mean that they're hiding the N inside the flux. So if you want to figure out, that's the math version. And like I said, it's a pretty simple equation. It just means you need to have an expression for the flux, and then you take a derivative of it with respect to time. So like, if something is moving at some velocity v, you're going to take the derivative, and the v is related to that derivative. Or if a thing is rotating, you would need to know, what's the angular speed of the rotation, and that's going to appear in connection with this derivative, that sort of thing. The harder part is figuring out the direction of the result, like conceptually speaking. So one thing that I want to emphasize, which I've made this note at the bottom, that to figure out the direction of the induced EMF, you can go through this chain of reasoning as described in Lenz's law, and I'm about to get to the examples. But you can also always just think about QVB forces. There's always going to be some kind of a relative motion between the field lines and the wire. And if you keep that relative motion in mind, and you think about F equals QVB, QV cross B, you can figure out the direction of the force on the particles inside the wire, and that tells you which way the current is going to flow. So you can think about it that way too. And I'll discuss both of those ways of doing it. So here are some general examples. I'm going to do each one more specifically. If you want to change the flux that passes through a coil, thinking about the fact that flux is integral B dot dA, there's a few different things that you could mess with. I could mess with the area. I could mess with the magnetic field. I could mess with the angle between them, because that changes the dot product also. So here's some possibilities. Change the area A. Make it get bigger or smaller. You could cause some rotation that messes with dot product. You could physically move the objects around. So like if I take my coil from one place to a different place where the field is different, that's going to change the flux. You could also change the strength of the magnetic field itself without physically moving anything. So like if I have a coil that's inside an electromagnet, if I change the amount of juice that the electromagnet gets, that changes the strength of the field. I wouldn't have to like physically pull the coil out or anything like that. But that would also change the flux if I change the strength of the field. So, example number 1. If we are changing the area of the loop, here I have my original loop, and then magically it grows into this bigger loop. I've tried to draw this kind of like a little bit in perspective, so we're looking almost edge on. If I hold up my calculator here, you're looking at it almost edge on, but I guess I should face it this way. That way it looks like the other shape. So I drew it kind of like as a trapezoid. The shorter vertical side is the one that's further away, and the longer vertical side is the part that's closer to you. So if the loop magically grows bigger, the Lenz's law way to do this is to say, first, what is happening to the flux? Well, when the loop gets bigger, it's now catching more field lines, so the flux is increasing. So I know that the rightward flux, you have to think about the directions. I know that the rightward flux increases. That's the thing that's happening that causes everything. Okay. I know that the end result, the direction of my induced EMF, is supposed to try to counteract that change. So the rightward flux is increasing, it's getting stronger. Therefore, I should try to reduce the rightward flux. I want to do the opposite of whatever is happening in the first place. So that means that I need to make leftward flux, because that way I can kind of cancel out some of the new rightward flux. And now that I know which way I want my induced flux to go, now I can figure out which way the current's going to flow. So I'm going to think about this front edge, the close vertical edge of the loop. And I have to use a right-hand rule now. I know the current is either going to be flowing up like this or down like this. In one of those directions, if I think about the magnetic field produced by the current, again, if my thumb is the current, I'll point it at you for a moment here. If my thumb is the current, then my fingers show which way the magnetic field produced by that current goes. What I want is to make a magnetic field that passes through the loop to the left. That's how I can get this leftward flux. So I'm going to hold my hand in front of my own screen here so that I can think about this clearly. But it seems like if I have my thumb pointing up, thinking about the close side of the loop, if my thumb points up, then my fingers that are inside the loop are pointing left. Therefore, on the close edge, the current needs to go up. Conversely, on the far edge, in order for the magnetic field of my current to be going left, I would need my thumb pointed down, and so on. So the current on this close edge goes up, then it heads into the screen along the top edge, and then down, and then back out of the screen on the bottom edge. And again, that will create an induced magnetic field that points left, which counteracts the original change. So again, that's all kind of convoluted. The other way you can think about it is in terms of the QVB forces, as I said. So what you need to think about here, I'm going to imagine just the top wire. So let's pretend that that circle is the top edge of the loop, and I'm just drawing it as a circle because it's like pointed directly at or away from you. So you're just seeing the circular cross-section. I know that the magnetic field points this way. As the loop grows, the top wire is moving up. So what I want to do is think about the particles. I should use a green for that. I want to think about the positively charged particles in that wire as the wire is moved up. And I can do QV cross B. The V is up, so I'm going to point my entire hand up. The B points to the right, so I'm going to twist my arm around in a funny way so that I can bend my fingers to the right. And when I do that, I get my thumb pointing into the screen. So the force exerted on the positive particles of the wire is going to go into the screen. And that means that the direction of the current, conventional current, which is made of positive particles, is going to be into the screen, because there's this QVB force on those positive particles that pushes them in that direction. That's what the EMF is. This induced EMF is just a way of thinking about the magnetic force that's exerted on the particles of the wire. And so notice that that corresponds with what I got by doing the flux reasoning. So you can think, what's happening to the flux? What do I need to do to counteract that? Which way must the current flow in order to get the desired field? Or you can think about this relative motion and do QVB. Always going to give you the same answer. So here's another example. This is involving a rotation. Most of our electrical generators are based on rotating loops of wire inside magnetic fields. So I have a magnetic field pointing right. I have my rectangular loop. Again, I drew it like a trapezoid so that it's a little in perspective. And the idea is that I'm going to be spinning the loop this way. It's hard to spin it without also changing the size. But it's like this, and I'm going to be rotating it that way. Whoops. What did I do? There we are. So the rotation is this direction. So in the moment that I have it drawn right now, here I'll also draw on I'll draw on my area vector. Instantaneously, at the moment that I've got it drawn, the amount of flux should be increasing because the area vector is at an angle with respect to the magnetic field, but they're getting more parallel. You could also think of the cross-sectional area of the loop as increasing. I only care about the horizontal part of the area because that's the part that's lined up properly with the field. So as the loop turns this way, its vertical extent increases, which means I'm catching more field lines, which means the flux is increasing. So let's do the Lenz version first. The flux is getting more positive. I don't exactly want to call it a rightward flux here because the flux is parallel to the A vector, which is not horizontal. But it's becoming more positive because the A and B vectors are getting closer to parallel. And so it's getting more positive. So therefore, what I want to do is want to make negative flux. That will counteract what's happening. So to make a negative flux, I need the induced current to generate magnetic field which goes opposite to the A vector. Instead of parallel to it, I want the induced field to be anti-parallel to the area vector. So if you think through some right-hand rules, you will find that that means the current needs to be going that way. And then it goes into the page over there, and then down, and then back out of the page down here. And you may be noticing that that's the same as on the last example. If I go back, I didn't draw an A vector here, but let's say that that was A. Like, it's almost exactly the same situation. I have a positive flux that's getting more positive, and that created a particular direction for the induction. And the setup here is basically the same. The other way you can think about it, if you want to do it in terms of the forces, the force version, I'm again going to think about the top wire. And this is again going to be pretty much the same thing. If you think about the motion of that top wire, it's not going straight up this time because it's being like rotated around. But instantaneously, the velocity is maybe something like that. And so if you do your QV cross B, the V is all this way, the B is horizontal. So there's everything, there's B that way. And so the thumb, dang it, everything gets reversed. From my perspective, my thumb is pointing away from me. It's towards you on the screen. But if I go this way, there's V, there's B. And so my thumb is pointing, is that all right? Yeah. So my thumb's pointing at the camera. Now I feel like there's still some reversal going on. There's too many layers of mirroring when I try to do this on the screen. So just think about the diagram. Ignore what's going on in my camera bubble. But when you do the V cross B, you should again get inward for the force that's exerted on the particles of the wire. Therefore, you get the same current direction that I said above. Okay, example 3. I'm going to be like physically dragging this loop of wire out of the magnetic field. So the blue box is a big region where there's a uniform field. I'm saying that that field points into the screen. And the loop is being pulled out at some constant velocity v. Although I guess it could be instantaneous, so it doesn't really matter. So according to Lenz's law, I know that there is flux through the loop. That flux points into the screen. So there's like an inward flux. But when I remove the loop from the field, I am getting rid of that flux. It's approaching 0. It was inward. It's approaching 0. So I have a decreasing inward flux. Therefore, I want to make inward flux. Now notice in the last two examples I had an increasing flux, and so I created an opposite one to try to decrease it. This time the flux is already decreasing, and so I want to reinforce it by making more in the same direction. So I want to make an inward flux. So if we think about, say, the left edge, I'm going to do some more right-hand rule here. I'm not going to do it in front of the camera because that's going to mess me up. But I want the flux on the interior of the square loop to be into the screen. And to get that, I need the current to flow up on the left edge. If the current is flowing up on the left edge, then the induced field has x's over there and dots over here. And that's what I need. I need to make x's to reinforce the decreasing inward flux that I started with. So the current on the left edge goes up. So I ended up with a clockwise current here. If instead I were pushing the loop into the field, then I would get a counterclockwise flux. Or if I reversed the direction of the uniform field B, that would also reverse the direction of the induced current, etc. If you want to think about the force version, it is pretty easy this time. I have this wire. I know that the wire is going that way. And I know that the magnetic field goes into the screen. So right-hand rule, V is to the right, B is into the paper. That gives me a result with my thumb that points up. And then lastly, this time I'm not going to physically move any of the objects, but I have this wire loop. It's in this uniform, for simplicity, magnetic field B. You can see the B is made up of dots, so the B is pointing out of the screen towards you. And I'm going to have B getting weaker over time. And the way that I can represent the magnitude of the field getting weaker is to spread out the lines. Remember, the density of your field lines tells you about the magnitude of the field. So if B is getting weaker, that means the lines are spreading out. I have the same wire loop, but the field lines are sparser. And you can quite literally think about this as if the lines were spreading out, just like when I was resizing it. So some of the lines are moving up, some of them are moving down, some of them are moving left or right. But the lines themselves are moving. So there's a relative motion between the wire and the field. So that's for when we do the force version. But let's do Lenz first. I have an outward flux, and it is decreasing because I have fewer dots. I start out with a lot of dots, and then the number of dots is going down. Therefore, I need to make more dots to try to replace the ones I lost. I want to make outward flux. And if you go through your right-hand rules, the way to get an outward flux is for the current to flow counterclockwise. CCW is counterclockwise. For the force version of the same thing, this is a little bit tricky because in QVB, V is the velocity of the particle relative to the field. But this time there aren't any moving particles, at least in like my rest frame. There's no moving particles, instead it's the field that's moving. So you have to sort of like reverse the direction in your mind. If I pretend that the field is stationary, let's think about the top wire. Here's a line for that top wire. If you imagine riding the top wire, you're sitting on the top wire as the field expands past you. It's going to appear as if you on the wire are moving downward through the field. The field lines are moving up past the wire. That's equivalent to the wire moving down past the field lines. So I have all these dots for the field. And the field moving up is equivalent to the wire moving down. So I'm going to say that the V for my cross product is down. B points out of the screen. That gives me a force to the left. I should draw my current in green. And again, that is in agreement with what I got by doing the Lenz's law version. So that's my last example. Personally, I prefer the QVB approach, which you might have already gathered. I think it's a lot easier to think about than the like multiple logical steps that you need to get a correct conclusion from Lenz's law. But you still need to be familiar with Lenz's law because you're going to run into exam questions that say something like, you know, what's happening to the flux in this loop? So you still need to be able to think about which direction is the flux and whether it's increasing or decreasing in magnitude. And you need to be able to make conclusions based on that also. But if the question just says, here's a situation, and which way will the EMF go, or which way will the current go, you can use either approach in that case. If they don't specifically ask you about the flux, then you don't have to think about the flux if you have another way of answering it. And personally, again, this is just me, I think that the QVB way of answering which way does it go is easier. But they will both work as long as you don't make any mistakes. I think there is more room for making mistakes with Lenz's law than with the force approach. And that's why I like the force approach better. All right, that's it for this one.